December 2024, OpenAI launched 12 Days of OpenAI, releasing a series of products and programs. The second day of release stood out is talking about reinforcement fine-tuning. Hi there, my name is Will, a software engineer at Google. In today's video, let's talk about fine-tuning. Fine-tuning is the process that taking a pre-trained model and customize it for a specific task or dataset. You can imagine you are hiring a new person into your company. This person may have industrial standard knowledges, but they doesn't have any knowledge around your company internally. You need to let this person ramp up by reading some internal documents or taking some training session before they can start their work. In the AI world, pre-trained models are new hires. In order to let models take effect in your task, you need to train them further based on customer dataset. This process is called fine-tuning. Training AI needs a lot of data. General models like GPT-4o are training based on the public text on the internet. But for companies and some research institutions, they have their own document repository, which is not open to public. In order to let AI work for these organizations, we need to let the model go through all of these private documents before it can start work. AI models can be tweaked, fit into any industries. That's why I think fine-tuning feature is more important than other products. Fine-tuning is a good start point of developing AI-powered application because it has many benefits. The first is cost efficiency. There is no need to collect large dataset and train from scratch, which can reduce a lot of cost for data storage and compute power. The second is reduce the training time, which can faster the iteration and reduce the time for product development. The third is adaptability. Fine-tuning that AI model can fit into any specific task with minimal additional training. This lets AI models can fit into any industries, solving real-world challenges and bring bigger impact beyond the model itself. Now, we know that fine-tuning can make model performance better, but how can we define better? We need a quantified way to measure the performance of a model. It actually depends on the task. For the classification task, we can use accuracy, and for the regression, we can consider use MSE, etc. Most of AI model today are using large language model, which is used for text generation task. In order to measure the performance of text generation task, we usually use BLEU or ROUGE. In order to get familiar with these two metrics, we need to understand three concepts first: precision, recall, and n-gram. Don't worry, they are straightforward. Precision is more about accuracy. It tells us how many outputs are correct in the model's output. If a model provides 5-word sentence and 3 words of them are correct, then the precision will be 3 over 5. Recall is a bit different. It tells us how many correct answers a model can find out. If there are 6 words considered correct, but the model can only find 3 of them, then the recall will be 3 over 6. N-gram are just the sequences of words. For example, 2 gram, just the 2 words together, like a cat. Okay, a quiz. How many 2 grams can a 5-word sentence be broken into? Leave your answer in the comment. Okay, let's go to BLEU and ROUGE to see how they work. BLEU is all about n-gram precision. It checks how many n-grams of model's output are in the n-grams of reference text. Let's calculate 2-gram precision. First thing first, we need to break this sentence into 2-gram sequence. Next, we need to calculate how many 2 grams are matched. In this example, 3 2 grams are matched. Since we are calculating precision, we compare the matched bigrams to the total bigrams in the model's output. So the 2-gram precision is 3 over 5. There is a loophole of precision. That is, the model only need to provide 2-word sentence, and both words are correct. Then the precision will be 1. In order to avoid that, BLEU introduced probability penalty, which prevent the model from cheating by generating overly short answers. ROUGE, on the other hand, focus more on recall. It looks at how many important n-grams from reference text are captured by the model's output. ROUGE is a family of matrices like ROUGE 1, ROUGE 2, etc. The number indicates which n-gram it focuses on. For example, ROUGE 2 focuses on the bigram. So in our previous example, the ROUGE 2 score would be 3 over 4. There are many ways to perform fine-tuning. I divide them into 3 categories: prompt engineering, regular fine-tuning, and reinforcement fine-tuning. Let's start with prompt engineering. In this method, we don't modify the parameters of model at all. Instead, we change the prompt to trigger pre-trained model's capability for specific task. It's more like the model knows how to do the task, but we need to find a way to tell model to do that. For example, we can instruct the model to provide output in JSON format by providing an example. Then the output can be parsed by the later programs. There are 2 directions of regular fine-tuning: the full fine-tuning and the parameter-efficient fine-tuning, which is PEFT. In the full fine-tuning, we change all parameters of a model. It's essentially train the model further. The key component in the full fine-tuning is dataset. We can provide a single task dataset, which let the model to training focus on one single task. However, there is a catastrophic forgotten of this method, which means the model become highly specialized in a single task and forgot its ability to handle other tasks. It's recommended to use multitask dataset to full fine-tuning because it can preserve the generalizability of the model. To avoid consuming a lot of data and computer power, we usually use parameter-efficient fine-tuning, or PEFT. There are 3 directions of PEFT. The first one is selective. In this method, we frozen most of data's parameter and training only a small subset of it. In this way, we can save a lot of data and computer power. Reparameterization in fine-tuning refers to transforming the parameter space of a model to enable more efficient training process. One popular method is low-rank adaptation, or LoRA. In neural network, parameters are represented as matrices. The training process is practically finding the changing matrix that will be added into the parameter matrices. LoRA breaks down the changing matrix into smaller low-rank matrices. Then, we only need to calculate these low-rank matrices. The trainable parameter will be much smaller compared to the original changing matrix. For example, the weight matrix has dimension 64 times 16. The change matrix also need to be the same shape. Then the total trainable parameters are 64 times 16, which is 1024. Then we apply LoRA with rank as 8. So we have A as dimension 64 times 8, and B has dimension 8 times 16. Then the total trainable parameter will be 640. See? It's much smaller compared to the previous one. The third direction is adaptive fine-tuning. There are 2 ways. The first, we can add new layers into the model. Then we only need to train the new layers and keep the model frozen. The second way is we adding a prefix embedding for every input sequence. This embedding prefix are trainable, and they have no meaning in the real world. We just add it into every input so the model can perform better in the specific task. The new feature released by the OpenAI is called reinforcement fine-tuning. We already know what is fine-tuning, but what is reinforcement learning? In traditional machine learning, reinforcement learning refers to the process that lets model interact with the environment. The model itself will improve during the interactions with the environment. The model usually takes an action and provides it to the environment, and then the environment will return the model with the next state and the reward to the model. What model need to learn is to learn how to take actions to maximize the reward it will receive. As for the LLM here is the model, and the environment will be the LLM context. Or you can say it as a prompt plus completion for simplicity. Now, we know that we want the LLM to maximize the reward it received from the environment. How do we know what's the reward it should return? The easiest way is to train another simple model that calculates the reward based on the model's output and actual result. In the OpenAI release video, they call this model as grader. With the reward from the reward model, we will apply reinforcement learning algorithm to guide the LLM to change itself. Then, that's the reinforcement learning fine-tuning process. Let's look back to see what we covered. We start with explaining what is fine-tuning and why it's important today. Then, we look at how can we evaluate the model's performance. After that, we discuss the techniques that can be used for fine-tuning, including prompt engineering, regular fine-tuning, and reinforcement learning fine-tuning. Fine-tuning is a key step in building AI-powered application. If you'd like to learn more about how to build AI-powered application, you can see my previous video. If you enjoyed this video, please subscribe and like. Thanks for watching. I will see you guys in next video.